So, this is the first of 7 talks that we're going to give for the Junction Festival in Clonmel. Very happy to be here, and I think before we start our talks, we should explain why we, as artists, would be taking on this particular subject, which is light, which is generally, and most of what we're going to be talking about is science, really, isn't it?
Well, way back 20 years ago, Dennis and I got very interested in the role of the spectator in art. And the spectator is all about looking, really, isn't it? As artists and as architects, we ask people to look at things. And so a natural corollary to that is visual perception, the eye, how we look and how we see, and of course light is our medium. And so naturally we evolved towards exploring this question of light.
We've taken that very seriously. We've explored every aspect of light, and we've explored a lot about
we're doing it now.
About perceptive psychology related to vision.
And so we went to Crawford Gallery last year, or maybe 2 years ago, and we said, would you be interested in doing an exhibition about light, but about all the light in the universe? That exhibition is called Invisible Light, and we're preparing it now. And these talks are the result of the investigation that we've done over the last 2 years to create our research.
Yeah, which has been quite extensive, really, hasn't it? And it has involved us looking at a lot of science, really. And we're going to try and present some of this science now. In fact, in the first talk that we're going to do now, we're really just going to look at the general idea of light.
The history of light.
Yeah, and how the idea of light has evolved over 400 years.
That's right. The exploration of the nature of light, essentially, starting with Isaac Newton.
And Isaac Newton would have been the father of modern science. And one of the first experiments he did when he was a very young man was about light, was about the nature of light and the nature of colour. So
maybe more than 400 years ago, no, not quite 400 years ago, Isaac Newton in 1665, he was at home, in his family home, because there was a pandemic in the world. There was a worldwide pandemic that had been lasting over 200 years at that stage.
200 years?
Yeah, the pandemic of the bubonic plague. And it kept re-emerging as regional epidemics here and there. And in 1665, there was one in London that spread to Cambridge. And so Isaac Newton, who was a student in Cambridge at the time, went home to his family home, and he decided to do some experiments as scientists do. And this particular...
So they involved prisms, didn't they?
That's right. So Isaac Newton had access to a couple of prisms, little glass prisms. At the time they were really quite common because they used them in chandeliers, they used them as novelty toys.
So these wouldn't have been optical prisms?
I don't think they were. I think they were just, sort of glass playthings, really.
Okay.
And so he set one up in his bedroom. He closed his shutters and bored a small hole in the shutter and allowed a ray of light through. He set a prism up so that it made a rainbow. It produced a rainbow on the wall opposite.
So that wouldn't have been the first time somebody would have produced a rainbow with a prism, was it really?
No, they did it all the time, and they thought at the time that these prisms coloured the light. So they were playthings, really.
Okay.
And so he set one up to produce the rainbow. He placed the other in such a position as to receive the rainbow, and it recombined it into a ray of white light that came out the other side. But the thing at the time is that Isaac Newton was a proponent of what was called the corpuscular theory. He believed that light was a stream of particles, basically something like tennis balls or cannonballs.
Cannonballs, maybe, yeah. So that would have been consistent with his vision of the universe, things travelling in straight lines to space at the same velocity until they came across other things off which they would have hit off or rebounded, and they would have passed energy onto. And so the corpuscular theory was consistent with Newton's vision of the universe. But it wasn't particularly consistent with the experiment that he was doing with prisms, was it?
No,
really?
because he was exploring refraction.
Yeah.
There.
And there was no way to explain refraction with corpuscles or with particles, really.
That's it, exactly.
Yeah.
And then a lot of other scientists were concerned about that. They said, well, hang on a second, this corpuscular theory is not really explaining refraction. Why, when something goes through another medium, why does it bend or change? They didn't know that.
And in fact, that's essentially what's happening when the rainbow comes out. Is it's bending, but it's bending at a different angle when it's blue than when it's red. And interestingly enough, when Newton published the results of his experiment, one of the things, they didn't really produce pictures of the experiment, nobody was there present, but they had to publish it in a way that other scientists could reproduce it. And I read that a lot of other scientists did try to reproduce this experiment with the prisms, and they failed.
Oh, really?
And Newton said the reason you failed is that you were using Italian prisms.
Oh, really?
Yeah, and if you'd used London prisms, you would have succeeded. So
a bit of chauvinism.
Yeah.
So, but anyway, there was a lot of other scientists at the time who were very concerned with this issue of refraction, and they didn't really feel that the corpuscular theory explained it fully. And particularly a very important scientist called Christian Huygens.
I think we're pronouncing that wrong. I think we have this document that says.
Now there was a Dutchman, and the name of Dutchman was Christian Huygens. Huygens. And this gentleman suggested that perhaps light are not particles, that they are waves. And this guy came up with a genius idea, which we now know as Huygens' principle. At least you call it Huygens' principle. But we don't call it Huygens' principle. You see, this sound, UY, is pronounced in Dutch as ui. None of you can say ui unless you're Dutch. To make it worse, this sound you don't have either in English. That's a ch. None of you can say a ch unless you're Dutch. Let alone that you can say the combination Huygens. Anyone who comes forward to me after this lecture and who knows how to pronounce the word Huygens has to be Dutch. I will be kind to you and call it today Huygens' principle.
And so Christian Huygens wasn't convinced at all. In fact, he was a senior of Isaac Newton, a little bit older, and he himself had developed his own treatise on light, where he put forward a wave model.
So waves, as opposed to the corpuscles we looked at earlier, are really just something that, at least in the vision of Huygens, and really in our vision still today, are just something that pass through a medium. They're like energy passing through a medium, a string or a surface of water or a body of water or even through the air as sound.
And he wrote to Newton about this, and Newton was getting very, very cross. He was sick of people disagreeing with this theory, and so he actually fell out with Huygens over it. He wrote to him like a schoolboy, apparently,
I read that Newton had a terrible character, and he was constantly taking people down. But Huygens is, when we look back on it now, it seems that Huygens had a very convincing explanation for refraction, and he should have been listened to because his wave theory really explained very clearly why it was that light, when it hits the surface of glass, that it bends, and that was really that the wavelength changes when it goes into the glass. And his diagrams really showed very, very clearly why it would be that if the wavelength changes, the direction will change. And all of this was worked out in a very, very sort of graphic way. Why
would you think the wavelength would change? Because
I guess because the material becomes more dense, the medium changes. So they would have observed.
Well, I would have thought that it's because the light loses a bit of energy. It goes into something else, and it dissipates some of its energy, and so slows down a little bit, maybe. And I think that was what Huygens thought. But Isaac Newton had the opposite idea. He thought that it speeded up.
That brings the speed up when they go to
That light would speed up.
I guess you could see like the way the sound would speed up if it goes from air to metal, for example. yeah.
Anyway,
so anyway,
Huygens-
there was clearly something going on that was explained by waves, but that wasn't explained by this corpuscle theory of Newton's.
Isaac Newton had such an incredible reputation at the time that his corpuscular theory was the one that was more or less retained
For a century, at
for
least.
a whole century. And so poor Huygens, they just put his treatise on the shelf for about a century.
And everybody forgot how to pronounce his name.
Huygens!
Okay, so about 100 years went by.
Yeah, they basically shelved Huygens' work for about 100 years. So,
And then around about 1801, another Englishman came along by the name of a young Englishman by the name of Thomas Young.
Yeah, very bright young fellow he was. So Thomas Young was a child prodigy, and he was so bright that he had read and understood all of Newton's writings on physics by the time he was 13, as well as speaking 10 languages.
Wow.
Incredible kid. And so he had a problem with the corpuscular theory. He was not 100% convinced that light was a particle because of diffraction. He had observed diffraction.
So the particular thing that he used, and he came up with a very famous experiment, didn't he, called the double slit experiment.
That's right.
And we're going to come back to that a couple of times later in this talk. It's very important. This is the central, the linch point of the whole theory of light in modern physics.
So will you describe it, the double slit experiment?
So the double slit experiment used diffraction. Now the diffraction is something that happens to waves when they pass through an aperture, and the aperture has to be quite small, like something in the same scale as the wavelength of the wave.
Okay.
And when they pass through that aperture, they radiate out from that aperture.
In fact, the aperture becomes the beginning of a new wave.
That's it. Yeah,
essentially.
yeah. So if you've got two slits side by side, like Young had, you've got two slits from which waves are radiating out from. And the waves,
so he sent one wave of light from a point source towards the slits, and two waves emerge from those.
So the other thing that happens on the other side, then when you get these two radiating waves, is they interfere with each other. This is the principal way in which we know something is a wave, really. It's like a litmus test of a wave, that it makes an interference pattern.
I love this demonstration. It's so beautiful.
Yeah. So if you imagine you've got a plane, like Young would have had, in front of this, projected onto this plane in light were a series of stripes, which were the two slits onto the wall, but not just two slits projected onto the wall, but a whole series. And this was the interference pattern.
Okay.
And this was the kind of a litmus test that proved, at least for Young, they proved that light was
behaving like a wave.
Was a wave, or was behaving like a wave. And at that time, it was either a particle or a wave.
Okay.
It couldn't really be both.
So across the channel, another young fellow called Augustin Jean fennel, who was actually
he was an engineer, really, wasn't he?
He became an engineer eventually, but he was not a child prodigy at all. In fact, he was considered to be very, very slow. By the time he was 8, he couldn't read and write at all.
No.
And the only thing he could do, in fact, he was very expert at making bows. He would go to the wood close by,
like
and
bows and arrows.
Bows and arrows, yeah.
Right.
And he made such fantastic bows that they were very dangerous. His parents had to take them away, but he learned. Well, I think now we consider that he learned all about waves and resonance with these bows when he was a small child, and he came up with this amazing experiment. It's so simple, and this is something you can actually do as well. We could do this here in our living room. Do you want to describe it?
So Fennel's experiment, which was like a similar idea to what Young had done, but he wanted to. It said there was a single beam of light, and in the single beam of light he put a metal disc. Like about the size of a coin, and he predicted that what would happen on the other side of the coin, rather than that you get a simple shadow of the coin, you would get at the center of the shadow a bright point of light.
And we see it here in the demonstration.
Yeah.
Beautiful.
Yeah. At the time, that was all he was expecting, was a bright point of light at the center, and this would have been caused by diffraction, essentially.
And so what he did is he described this, and he wrote it as part of a submission to the Academy, the French Academy of Science.
For a competition, wasn't it?
A competition, yeah. And they were very skeptical, but very impressed, and they decided
because
to
the
do
French
it.
Academy was Newtonian at the time. They
That's
believed
right.
in corpuscles.
Exactly.
Yeah.
And they decided to try it out, and they carried out the experiment, and in fact they did get this point of light, and also they got interference pattern at the edge. And
Something that looks a bit like this.
Yeah, so they
Quite beautiful. So Young, depending on what world you're in, if you're in the British Anglo-Saxon world, you talk about Young's slits. If you're in France, you'd probably be talking about Fresnel's
Fresnel.
rings. Right. And they're the same thing, really. They're a diffraction pattern that is a kind of a proof of the wave nature of light. Yeah.
So from this point on, the world of science was quite convinced that light had a wave nature. They were pretty much convinced. But that brought up a whole series of other problems because waves have to go through something.
At least in the 19th century conception, and pretty much today as well, a wave is a form of energy that travels through a medium, isn't it? So if you look at the sea, if you're standing on the shore, you look at waves coming towards you, but the sea isn't coming towards you unless the tide's coming in. The waves are coming towards you, but the sea stays where it is.
That's it, exactly. So they went back to an old concept. I mean, I think a lot of scientists had played around with this idea of ether, stemming way back to classical times, the idea of a luminescent ether, or luminiferous ether, that filled the universe.
And this ether, unlike the ether of the Greeks, was only there to carry light. Essentially. So in order to, the 19th century physicists, especially British physicists and to some extent American physicists, became obsessed with the idea that they needed to prove or come up with some evidence of the existence of this ether. And in fact, it was probably a Frenchman who progressed most at the beginning.
Fizo, in fact, yes. So Fizo figured out that
he had a beautiful name, didn't he? Hippolyte.
Armand Hippolyte Fizo. The French have the best names. So his idea was that, well, if we're a moving body in space, which we are, the Earth is moving around the sun, and we know that, and we're in this bath of ether, then we must be moving relative to the ether. So that must create some sort of wind. As if you're in a car and you put your head out, you feel the wind on your face.
And they called it wind, or they called it a drag?
Ether drag. Well, they had the wind. The ether wind is the wind, the movement in relationship, the wind that you would feel. But then the ether drag.
That would be the resistance of the ether.
The Earth would then drag it along a bit. Imagine if you're a boat in water, you still move the water a bit with you. So they said, okay, so the ether will be moving relative to it, but not entirely, because we'll be dragging some of it a bit with us. But there still must be some relative movement. Very complicated.
But no matter what experiments they made, they could find no evidence that there was anything but empty space.
First of all, in order to see if they thought the only way they could prove it was by verifying if the speed of light changed in different directions, because if the light was moving with the ether, then it would not be going at exactly the same speed as light that's moving against the ether.
Okay.
So
a little bit like sound, the Doppler effect, isn't it?
Yeah.
When you're moving towards the sound, it's coming at you quicker. If you're moving away from it, it's becoming slower.
Exactly. Exactly. And so to be able to prove this, first of all, they had to be able to measure the speed of light. And
so they came up with fantastic methods for measuring the speed of light, didn't they? Fizo
came up with a very clever little method. So Fizo's idea was he would set up a beam of light and project it 8 kilometers to a mirror, but it would pass through a moving wheel. And so initially it didn't pass through.
This is like a lighthouse sort of thing.
Initially it didn't pass through because it wasn't going. The wheel wasn't moving fast enough, so the light would hit, the spokes or whatever. So he speeded it up until the light passed through. It then would hit a mirror and then come back, be reflected back, and he managed somehow, I don't know quite how he did it, but from that experiment he was able to measure the speed of light.
Quite accurately as well.
Quite accurately, very accurately. 5%, up to 5% accuracy, so very, very accurately. So he did that, and then he decided, okay, now I know what the speed of light is, I can do an experiment in moving water. And so he set up a whole other apparatus where he shot light through moving water going in one direction, and then a beam of light in the other direction coming back.
Okay.
And he measured those, and
He measured the speed of light in water
Yes.
against the flow and with the flow.
and with the flow.
Yeah.
And
what did he get?
Well, just a little difference, not enough to support, his theory.
Right.
Which was a pity. So that was a bit problematic because it didn't really support the theory of the ether. It was very frustrating. So next we have Michelson and Morley.
Right.
So Albert,
Great names
Michelson
as well.
and Edward Morley, two Americans, and they were very, very concerned with this question as well. And so they came up with a much more sophisticated organization to try figure out if there was this ether wind and this ether drag. And so they set up their installation, which consisted of a 45-degree mirror to which they would send light, and part of the light would go through. It was partly transparent.
Right.
Part of the light would go straight ahead, and part would be deviated through 90 degrees.
So that was like presumably in one direction the ether was slowing the speed of light, and at 90 degrees it would not be.
Well, that's what they were trying to test. Yeah. And this, in order to not have any other interference, they came up with this incredible system where they put their installation on a giant block of granite, and they floated this block of granite on mercury.
Mercury?
Totally mad, yeah.
Same.
Yeah. And so they set up this whole installation and tried it all out again. And once again, it didn't really work. I mean, they got a little difference, but not enough to...
In fact, despite the fact that they were using an instrument that was much more accurate,
they got a similar result to
failure.
Fizo. This is known as the most famous failed experiment in history.
And it left everybody totally flummoxed, really.
No proof of the luminiferous ether at all. But a very clever Irishman had an idea, and this was I'm going to where am I
Fitzgerald, wasn't it?
Yes, George Francis Fitzgerald. And so he was a professor at Trinity, and he wrote a letter to the Scientific Review at the time and said, he suggested that if moving objects were foreshortened in the direction of their motion, then this would explain the differences in results that they were getting. So imagine like a train, a TGV, a really fast train is moving, through the countryside. He suggested that in fact that train will be a tiny bit shorter while it's moving than it is.
So this sounds like Einstein, doesn't it? But it would have been before Einstein.
Getting close to the theory of relativity.
But this would have been quite a few years before.
This was in 1889, actually.
Right.
So it's like a long time before.
15 years before.
So a lot of people were throwing ideas around, weren't they?
I mean, and absolutely no success in proving the existence of the luminiferous ether. But nevertheless, particularly the British Academy were absolutely devoted to this well into the 20th century. But what was happening on the continent in the meantime is there was lots of doubt being cast on the idea that light was a wave form. In fact, they discovered, and they were studying something called the photoelectric effect.
Okay, yes, that's Hertz came up with that, didn't he? Yeah.
Hertz was the first person to really study it seriously.
Showed, what that effect is when you've got a piece of metal and it's hit by certain forms of radiation, particularly ultraviolet light, it emits electrons. I believe he showed it by creating a sort of a spark gap, so between two metals, and when he bombarded them with electrons, a little spark would jump across the gap. So
these were like little experiments, a bit like the double slit experiment. Not a massive experiment like the one that Michelson and Morley did, but nevertheless they were putting a lot of trouble in the way of the general theories that the fact that light could displace an electron, which they knew then was a particle, suggested that light was behaving like a particle.
Yeah, indeed.
And that really led to a German by the name of Max Planck to come up with a theory of light that was very close to a corpuscle or a particle, which he called quantum theory.
Okay.
Really. Yeah.
So he called.
So he
Quantums?
assumed that light was only came in tiny packages, which he called quanta.
Quanta. Okay.
And
Great.
these quanta, he didn't call them particles, but he said that light could only travel in these packages.
Okay.
He didn't really have any evidence as to whether it was as to what it was, but so he just called it a quantum.
He was a bit of a character, actually, Planck. Apparently, when he wanted to study physics, his professor told him that, oh, don't bother, there's nothing new to be done in physics. And he said, he told him that he didn't really want to discover something new. He just wanted to understand. So he went ahead.
Very
and then
wise.
when he came across, he did finally, make some very important discoveries. And it was difficult to get these across the line. People didn't necessarily accept it. And he made the statement that a new scientific truth does not triumph by convincing its opponents and making them see the light, but rather because its opponents eventually die and a new generation grows up that is familiar with it.
Okay.
So, anyway, he had a tragic life as well.
So, nevertheless, Max Planck's theory 5 years later became one of the bases of the most famous theory that we know in the early 20th century, didn't it? The Einstein's theory of relativity,
Oh, yes.
in which light had a very important place, and in which the idea of light as a particle was
Of
quite
course.
consistent.
Well, he links energy, mass, and the speed of light, doesn't he?
And the speed of light is the one constant. So,
And of course, this demonstrates that light can have no mass because as it approaches the speed of light, which it does, anything approaching the speed of light, the mass will become, enormously, gigantically massive. So it can't
and
possibly
that kind of put to sleep finally the idea of a luminiferous ether because Einstein was talking about light traveling through a vacuum and its constant speed really in the vacuum.
So we're 1905 and we're at the position where we now know that light has a wave function, but we also know it behaves like a particle in some ways.
But it's a very particular particle because it can travel at the speed of light. And now, according to Einstein's theories, anything that travels at the speed of light can't have any mass.
So light is a particle with no mass that behaves like a wave.
So here we've got into a part of scientific history when there's paradoxes, there's things that just don't work in common sense. I mean, how can we conceive of a particle that has no mass? The particle, as we showed it, as we imagine it, is like a little cannonball. So if we consider a massive particle like a proton, it's a big cannonball. And we consider a tiny particle with a much smaller mass, like an electron. You just put it beside it as a much smaller cannonball. But then you consider a photon. A photon has no mass.
With no mass.
You just have to consider it as
So
a particle.
does it exist?
Does it exist at all? Yeah. So
Complicated.
we enter into a time of paradoxes and of thought experiments.
That's right. So a lot of mathematicians and physicists started to carry out these thought experiments because they couldn't actually physically do these experiments. That led them to understand the nature of light a little bit better, didn't they?
And these thought experiments were not so much demonstrations as analogies, really, mostly. Like you had, for example, Schrodinger's cat, which is
terribly cruel.
A story of a
Nasty
cat
one.
who never existed in a box, and you can't see the cat, but you've set up a mechanism that kills the cat. Or doesn't kill the cat, and you don't really know whether the cat's alive or dead. But as long as you don't know the cat's alive or dead, you have to assume that the cat is both alive and dead.
So that leading us towards the uncertainty principle.
That's really it's like an analogy for the uncertainty principle.
So if you don't know,
there was no cruelty to animals.
As long as you don't. Tell us about this one here, the one with the little bus or train.
Well, so this is one that always interested us. I mean, Einstein's thought experiments were about observers, really, and about considering how phenomena work according to certain inertial frameworks. So if you're an observer on a train, the world, a phenomenon like a lightning flash will look different to you than it will look to a person standing on the platform beside the train as the train speeds through. So the particular framework from which you look at things affects their nature, or at least affects the way you observe them. And he was particularly interested in things that were simultaneous and how they would appear simultaneous from one point of view but not from another.
So we're in an era of paradoxes. We've shown that light behaves like a particle and as a wave. I mean, in fact, the scientists have shown that.
Yeah. And not only that, but certain scientists were going a lot further. One of them, Wheeler, John Wheeler, an American astrophysicist, suggested that if we revisited Young's slits experiment, and we set it up differently, but this is a thought experiment again, so he was imagining revisiting it with modern equipment, and he set up this modern equipment instead of just having a wall on which you would have seen an interference pattern, that you had some sensors, and these sensors would tell you which of the slits the light had passed through. So Wheeler said, if you know which slit the light passes through, there is no wave function. It just behaves like a particle, and it just goes straight through.
And what would justify that? Why would he have that idea?
Well, so he was really just sort of using the quantum physics Copenhagen interpretation. In fact, that was going back to the uncertainty principle.
To our blokes in Copenhagen who said that you could not know everything about a particle in a subatomic level. And if you knew everything about it, then that would change the way it behaved.
Yes.
Yeah.
So exactly. So by adding which path information, that was the term that he used, by which slit, whether it's the left slit or the right slit, once you know which path it goes through, it stops behaving like a wave and behaves like a particle. That was what he said. And not only that, he went further than that. And this gets to the point where a lot of people said, whoa, this is getting a bit crazy. He said if you could turn your sensors on and off during the experiment, the moment you turn the sensors off and you don't have which path information anymore, the interference pattern comes back. The moment you turn them on again, the interference pattern disappears.
So this was speculation. It was a theory.
It was a thought experiment. Yeah. But what's happened since is several scientists have made empirical experiments in the real world, not thought experiments, where they've proven that Wheeler was right.
Really? Wow.
And one of them, the first one, major one, was with electrons, and not with light particles. And at the time, the advantage that they had was that electrons you could send one by one. Now, electrons also have a wave and a particle function. And they set up the double slit experiment.
This was done in the 1990s,
yes,
is that right?
That's it, yeah. And I think the one that we're looking at was done by a Japanese researcher, but it's been done several times. And they sent electrons one at a time through the double slits. They didn't have any sensors saying which path. First of all, they just seem to be making a random pattern. They're just passing through. They're being diffracted as the light was. So they're turning up somewhere on the screen in front, any place, and it appears to be just a random pattern. And then as you get more hits, it starts to appear an interference pattern. This is extraordinary because each of the electrons are being sent through individually. They can't be interfering with any other particle. There's only one electron in the air at any one time. So the question is, what is interfering with the particle?
That's blowing my mind completely.
Yeah, it does blow your mind, and it gets certain scientists are saying this is getting unscientific. Other scientists say no, this is quantum physics. The particle, the electron in this case, interferes with itself.
Wow. Okay, moving on.
And then we came at the beginning of our century. Several scientists, once again. One of them, a very nice French scientist called Alain Aspect, came up with an experiment called the quantum eraser, and this was with photons. This was with light, and it's a very complex experiment, so we won't get into it. But basically, this reproduced Young's slits experiment, we're using modern apparatus, using beam splitters, and with a long distance, you could switch off the second beam splitter while the photon was in the air.
So it would behave differently, even though it had started out on its path in one way.
It started off as a wave, it became a particle.
If you switch off the apparatus so you no longer know its path, it behaves differently.
Yeah. So this is why Wheeler called his thought experiment the delayed choice experiment. That in fact we are choosing the nature of the photon.
Oh, incredible! So this is the point we've got to. We've now looked through this whole history of the nature of light. We've seen that light behaves like a particle and behaves like a wave, but also it changes its behavior if we know what it's doing.
Yes, and we get to choose which it is, essentially. Yeah.
That is incredible.
So this when you get to this point, Alan Aspie is very funny, gives a very funny presentation, which we're going to look at a brief moment of now.
Here you have a equation. Do you behave like a particle? And then the photon says, of course. And then he behaves like a particle. And then, when you put this system in front of the photon arrives and say, haha, they're not going to fool me. I know there's a Mach there and the ferrometer. And so now it takes the dressing of a wave and behaves like a wave. So you keep the two apparatus behind your back. The photon arrives at the beam split and say, hey, what is the equation they are going to ask? And Mr. Wheeler say, I'm not going to tell you. Pass first, and then I will decide. That's the idea of Wheeler's delayed choice experiment.
That's incredible.
Yeah, or we can decide.
Such implications with regard to philosophy and art.
Exactly.
And, wow.
So we're talking about, this is what's called Wheeler's participatory universe. That the researcher is is actually deciding the nature of what he's looking at. And he would have, Wheeler would have accepted all the implications of that. You know, that even implying that the universe had begun, but it only really come into existence when people started to look at it. People started to look at it and understand it.
So the universe didn't exist before we could look at it?
That's kind of what the implication is. And obviously most scientists, most physicists would say,
putting forward creationism or any of this stuff here, but
so most scientists are very skeptical.
This would have, of course, fed into science fiction, into art in many ways. I think, into literature.
Yeah. And that was a physicist would say to you, well, this is a philosophical question, or if they wanted to be more disparaging, they would say, well, this is just science fiction.
But we still don't really know the full nature of light, I think.
But it's still just really a scientific debate.
And
obviously the arts.
Well, the arts, I suppose, have a role with interpretation. I mean, that's what art has always been about, representing and interpreting. So, and it's a big struggle to try and interpret the nature of light. Given the paradoxes that we've discussed. But we can make a little.
But paradoxes are. Ever since Wilde, we've loved paradoxes, haven't we? As artists, especially as Irish artists.
Oh, this is true. Anyway, so we've looked at the history of light, and we've come to the end of that journey, and we really are no wiser about the nature of light.
Maybe we're a bit more intrigued.
Yeah, I hope you're intrigued, and I hope that you'll come and join us tomorrow to talk about more about electricity and magnetism in relationship to light, which is the electromagnetic spectrum, at Junction Festival, which is fantastic to be here. And
hope you enjoyed today's talk. Thank you very much.